Next speaker is John Rust. As I said, the godfather of this event. He will be here late this week after he will resolve his passport issues. But now, John, thank you for your dedication to get up at an insanely early hour. And now the floor is yours. And thank you for dialing in.
Okay, well, thank you, Simone and Felix. And I would just want to say thanks to the University of Lausanne for putting this on. It's a big investment, a big contribution. We're all really grateful for what you guys are doing. And I'm also really grateful that so many high caliber students are there. I wish I could be there to meet you right now. But honestly, I had my passport was not accepted by Switzerland. So I took off. I was about to take off on Saturday night, and they said, no, you can't board the airplane because my passport expires in November. And it turns out that Switzerland is a Schengen country, and the rules are that your passport has to expire more than 6 months after your return date. So I had to get a new passport on a hurry. And but the American government isn't so efficient. I can't just go down to Washington. I live in Washington, D.C., but everything's backed up like weeks, 6 to 10 or more weeks. You can't just walk in. But they arranged for me to get a new passport. I had two choices. I could go to El Paso, Texas, or San Juan, Puerto Rico. So tonight, I'm flying to San Juan, Puerto Rico, and tomorrow I should get my new passport so I can fly out. You know, I wish I could tell you my dog died. I know you wouldn't believe that, but that's the honest truth. Okay. Okay, so this title is kind of it's got too many learns in it, but I did that intentionally because you know, we're going to hear a lot about learning, right? We're hearing it in many ways: Bayesian learning, machine learning, deep learning, Q learning, deep Q learning, supervised learning, unsupervised learning, offline learning, online learning, real-time learning. Have I missed anything there? Oh yeah, well, there's, you know, how people talk about it. They call learning by doing, learning the hard way, right? Or maybe your mother would tell you one time, anyone ever said, you never learn, you never learn. So not all of the uses of learning, it's a heavily overloaded term, okay? And I wouldn't say that all of them are to be learning in the human sense. In many cases in the machine learning, I would say they are algorithms to approximate a function or a solution or make a prediction. They're not learning in the sense that we think about in everyday life, which is considerably more complex. Now, that's not to denigrate what they're doing, but you know, real life learning, you know, potty training, right? Learning to tie your shoes, learning to drive a car, learning a foreign language, learning how to multiply numbers or play the piano, or learning what you want to do with your life. Each of these types of human learning may involve very different neural processes. For example, learning to play the piano probably involves very different parts of the brain and underlying mechanisms than learning a foreign language. In particular, I've heard people say that, you know, your hands, the neurons in your hands, I'm not a piano player, but if you're a good piano player, there's no way the signals can go from your hands to your brain and back. It's like you're downloading code within your hands to execute the keystrokes on the piano really rapidly. So really interesting decentralized processing and learning probably in your hands as well. Now, that's pointing out that human learning is vastly more complex than machine learning. We just don't have adequate models that are anywhere close to capturing the myriad ways that people actually learn and adapt. Human learning is intimately connected with experimentation and decision-making. And it's almost intuitive that they are so connected. They've done experiments with little babies, and babies are born, cognitive scientists believe, that they have basic, knowledge of physics. They have some basic information when they come out of the womb, and they already learned a lot in the womb, so they know about gravity, like things fall. And if anyone you had babies at various times in your life, you see that they're on the high chair and they love to push their sippy cup off the high chair and then laugh as it falls, and they do that for 5 or 10 times, and it's kind of a pain. But then the baby gets bored because it knows stuff falls, right? It's that's not a surprise. So they did an experiment at Johns Hopkins where they put a ball on an inclined plane, and inside this rubber ball was a magnet, and there's a high magnet. So they could turn on the magnet when the ball's rolling down the inclined plane and make the ball just freeze right in front. So initially they had the magnet turned off, and the baby would put the ball on the plane and watch the ball roll down the inclined plane. And they do it about 2 or 3 times, and the baby knows, okay, been there, done that, not surprised. The baby gets bored, wants to move on. But then in the middle, they would have the ball freezes right in the middle. They turn the magnet on, the ball will go halfway down, it wouldn't continue. And the baby wasn't expecting that. And the baby just automatically perks up and says, what the heck is going on? And it automatically starts to grab the ball and try to figure out what's going on. So, even babies know how to experiment. It's just an intuitive, and it's an essential part of data gathering. So when you think about what we do, there's a lot of things that aren't in the standard machine learning vocabulary. Like what's the interesting question? What do we want to learn in the first place? How do we get that information? What sort of method do we use and learn about this topic? And then we have mental models. So I'm a big believer, we model consciously, but I think our brains are full of mental models that we're not even aware of. I mean, what is a dream? A dream is kind of a really realistic mental model, and it proves that they just go on inside our brains without even our direct conscious supervision many times. And so we're formulating plausible hypotheses and designing experiments to test these hypotheses. Very, very complex. Probably really, really hard to totally get at that. So, there are some elementary theories of Bayesian dynamic learning that, there's a work by Wall that gave birth to dynamic programming on the sequential likelihood ratio test. And it's a fairly abstract and limited and oversimplified model of actual learning, even though it's extremely cool. But, we can't just criticize because, we have to start simple. We have to, and that's a basic principle as well. And designing a good experiment is a perfect example. Designing and focusing on a simple hypothesis to start and a good experiment to test it, that's a classic example of something of human intelligence that has propelled us forward. And today I'm going to go through a classic paper that designed a laboratory experiment, and the paper is titled "Are People Bayesian?" And it's by Mahmoud El-Gamal and David Grether in 1995 JASA. So I want to keep on time. I have some big picture questions, but then I'm going to go into their study and I'm going to reanalyze it and show how machine learning can be really useful in understanding how people learn, even though machine learning has its limitations. So I have to be conscious of time, but there is a cool book I like. I read a lot of cognitive science, and I think to really move forward in structural estimation in the future, not only is machine learning and computer science important, but neuroeconomics, cognitive science, psychology. There is a great amount of research and really cool work in these literatures. And what we call a structural model today with the utility function will be in 10 years considered like a very reduced form, right? It's, you'll be going down into the level of the neurons in your brain and the layers inside your brain that process things. And how much of this work is done, we're not even aware of. It's all it's being done. There's just our heart's beating and we don't even know, we breathe automatically. There's all these neural circuitry operating. And that book by Incognito is emphasizing that. Now, what's really cool is this idea of mental models, and I really believe this. And this is not a new idea. It goes back to 1956 when you think about visual cortex, and that, you know, if you think about deep networks, the visual cortex has many layers, and that's a classic area where the deepness of the network involves higher level of abstraction, right? The identifying pixels and objects, and then, you know, and there's some really cool videos for those of you who have gone to Blue and Brown. There's a really nice video. Fader told me about that, about recognizing digits with deep neural nets. And you don't need a very big neural network to kind of accurately classify images. And, you know, that kind of gives you a sense of shape, edge recognition, and recognizing a face and various things that the visual cortex does. But he says that the visual cortex is fundamentally a machine whose job is to generate a model of the world. And the reason that's, you know, makes sense to me is that visual processing, it's even the video is expensive, lots of pixels. And what, you know, if you think about Zoom, it's not sending all the pixels every minute. It recognizes that, you know, my screen is sitting there not doing anything right now. It's my voice, and it's only sending diffs of pixel diffs, and it's only syncing smaller amounts of information because of bandwidth. Well, the same thing occurs in the brain. And the brain is using a mental model of the visual, and then it queries. They call it on a need-to-know basis. Right? It's really essentially our consciousness of vision is like a hallucination. And you know, if something, you know, we forgot somebody was sitting next to us, well, what do? We turn our head and look at them. Oh, yeah, that's Bertel sitting next to me. Yeah, that's Bertel over there. Huh. So that's how it works. And you know, I think that's very cool. And there's another article, I won't really be able to go into all these quotes, but a guy named Joshua Tenenbaum at MIT called Theory-Based Causal Induction. And we're going to get into the question about whether, you know, how we learn. And unlike machine learning, which usually learns best with tons and tons of data, humans typically don't have tons and tons. We have small numbers of observations. And yet we do remarkably well by making inferences and very good choices with very limited amounts of information. So how do we train our brain with limited amounts of information? I think it comes back to mental models and internal simulations and counterfactuals that are going on in our brains all the time. And we're learning through simulations, which are counterfactual simulations. And that's why we don't do stupid things like, well, when I was young, I did a stupid, well, I don't tell you the stupid things I did with I'm a kid, but these days I, you know, do better. And I did a lot of stupid things, and, you know, and then I learned the hard way. And then, you know, then my mental model was upgraded, and then I got smarter. So the other thing I'd like to point out is, human learning usually takes a lot of effort. And, you know, when you learn new stuff, it's I remember when I was a grad student at MIT, and, you know, it was a challenge. You know, people said going to MIT, it's like drinking from getting a sip from a fire hydrant. It's just a force feeding of so much information. And at night, I would try to do my reading, so I would just fall asleep. My brain was processing all this information. I was exhausted. So that's because you're rewiring your brain. And when you're learning this process of altering neuronal connections, it takes a lot of energy. But once we trained, and after sufficient investment and practice, you know, things become hardwired, and it gets easier and easier. It becomes intuitive, second nature, quasi-automatic. And this is captured in Daniel Kahneman's 2011 book, Thinking Fast and Slow. And he talks about a system one, which is kind of the automatic knee-jerk, instinctive emotional system. And the system two is the more like, hey, John, you shouldn't do that. Don't do that, John. You know, it wouldn't be wise, wouldn't be prudent. It's more deliberative, more logical. And learning probably is involving more of system 2. But once you learn something, you hand it over system 1, and then it's like it's a subroutine that's automatically executed. Now, when you train a neural net, you see something similar, that training neural deep nets, and if you do them on your computer, you'll find that the fan goes on and the energy, you know, like on a Mac, it'll show the energy bar going up. If you're using your GPUs, yeah, they're going to be heating up the machine, because that's an energy intensive to train, because you're solving an optimization problem with lots of local optimum, and it's doing lots and lots of computation. That's why it's it's computationally intensive. But once, you know, and I think Simone kind of indicated this, once you've trained your neural net, execute, just evaluating it at any given point is really, really fast. And that has really big insights. And so it's true for humans, probably true for machine learning. And when Simone will probably be talking about surrogate models, a very exciting new idea for structural estimation, where you kind of estimate, you treat the parameters as an additional state value. When you solve it for that, and you get an entire surface, not only for the dynamic part of your model, but for all the parameters. And then you just evaluate the likelihood by maximizing the surrogate model. So I think Simone will explain it more clearly than I have. So I'm going to try to keep on time. I've gone, how much time do I have? I have 80 minutes, right? So what time do I end? It's 4:50. I'll try to keep on time. But I have, I'll try, I don't want to, because I can't see you. And then if you're all dozing already, then, so I might be like droning on. So I'll try not to do that. But basically back in 2018, Bertel hosted one of these, kind of the forerunner of these DSEs at Copenhagen, and it was on machine learning. And some of the same people here were at that DSE. And we got a special issue of the Econometrics journal because Jaap Aubring was there. And we wrote in an introduction article, a survey article. They were kind enough to let us do this, called Machine Learning and Structural Estimation, Contrasts and Synergies. And we started out, a section was titled, How does machine learning differ from structural econometrics, and will machine learning put us out of work? So it's a little bit tongue in cheek. So, but we were just, kind of joking that we're not worried that we're going to be put out of business. No, it's, maybe those people down there, but our jobs are safe. We're professors, these guys aren't going to, So we said that, we wanted to look at what the key difference is, and this is a quote here: the machine learning and structural estimation have a common interest in prediction and decision making. But the goal of machine learning is to enable computers to do these tasks, so it's more practical, whereas structural econometrics is focused on learning how humans do these things. So machine learning is actually, in some sense, more practically oriented in trying to automate tasks that previously only humans could do well, whereas structural econometrics, for a reason we discussed below in the article, has been more academically oriented in trying to understand and model human economic behavior. So it's another kind of learning called inference, right? We're using data and models and theories, and we're kind of hypothesizing. So we're theorizing and doing inference, which isn't quite what machine learning does. So, Simone talked about credit default. Now, here's a good example. Machine learning is predicting who defaults, right? The bank doesn't really care why someone defaults. It just wants to know who's going to default and what's it going to cost them. But in structural econometrics, we are more interested in understanding what causes people to default and what are the economic and legal institutions and conditions and incentives that affect the default decision. Like, is it rational default, right? Is it a rational default model? Or, is there an irrational component to default, right? Talk about strategic default and so on. Really interesting So I had a student named Yang Fan Son at Georgetown. He got big data on 37 million 30-year mortgages from Fannie Mae. It's the big GSE government, quasi-government organization. And he studied bankruptcy of individuals, and he had pretty cool data set. And what he focused on was the question that interested him is that in some states they're called non-judicial, which is kind of like it makes it easy for the bank to kick you out of your house and then put the house back up for sale. It's kind of expedited, push you guys out and send over the sheriff and kick you out of the house. But there's judicial states that you have a lot of rights. You can sue and hold up and hang out for years in your house, even though you're not paying the mortgage. So it's much more costly in judicial states to default, for the banks. If someone defaults, it's going to cost them. They lose more money. So Fannie Mae charges a premium for default. It's called the guarantee fee, but for some reason, they don't differ between judicial and non-judicial states. So in these hard judicial states where it's more costly, they're paying the same guarantee fee. So there's a cross-subsidization that Yang Fan, discussed in his thesis. And, but the question is that he was interested in a counterfactual. What would happen, if you stop this cross-subsidization and you charge more for the guarantee fee in the judicial states? Well, that's he was doing a counterfactual prediction on what's going to happen to default behavior and interest rates and welfare and profitability to the banks. So there are a whole bunch of actors involved, and that he used a structural model and got some very cool answers. I won't go into further, but this is a really good example of a counterfactual prediction. It hasn't, Fannie hasn't changed its guarantee fee. It's a uniform fee. So the question is, can machine learning do counterfactual prediction? And we gave an example of a thought example. Many of you heard of AlphaZero. That's Google's DeepMind's self-training deep Q learning network that became a world champion in chess with just a number of hours of wall clock time of training. Now, maybe millions of processors. So the actual CPU time might be pretty big, but it was trained in a matter of hours, according, if you believe Google, in which I pretty much do. So then you might say, well, how could you do a counterfactual in chess? Well, what happens if you change the rules in chess, right? Suppose you allow a pawn to move forward and backward, right? So, and it currently can only move forward, but suppose you just say, hey, let's see what happens to chess if pawns can move backward. Well, in principle, you could retrain, you could use that whole thing and say, what's going to happen to the game of chess? How does it change when you change that rule? And presumably the same deep Q learning process could do it and then tell us how the game changes, like what's the win probability and so on. Now, a more actual example is a kind of a cool paper that was done at the Resources for the Future. It's here in Washington, called RCTs Against the Machine. Can machine learning prediction methods recover experimental treatment effects? So this paper is also on the Dropbox, and basically, the gold, everyone says the gold standard is RCT, randomized controlled trials, and there's a lot of people like at Harvard and other places. I'll name a name, probably Larry Katz. There are people or Joshua Angrist, right, who just don't believe structural. Too many assumptions. I don't believe these models. So they believe an RCT. Well, yeah, I believe in RCT too, but it's sometimes really expensive to do them. You can't, if you're not a friend of the World Bank, you can't do an RCT. So the question is, can you use machine learning methods? And they find that you can. They're using things like not deep neural nets, but XGBoost, random forests, and lasso. And what they say is, we find that machine learning counterfactual prediction methods can replicate experimental treatment effects remarkably well and with relatively little data on predictors. And I'm saying, whoa, because it takes us a long time to do these structural econometrics models. And then people don't believe them anyway. So I'm wondering, is structural econometrics already obsolete? We tried, we noticed the angst, and there's a part of this general angst, with ChatGPT, people are getting freaked out. I mean, it's now, maybe I'm getting a little freaked out, except I'm 68. So I guess my human cap, maybe I'm already obsolete, but there's a paper I think by Larry Kotlikoff and Benzel called "Robots Are Us: Some Economics of Human Replacement," and their conclusion, the start of their paper: will smart machines do to humans what the internal combustion engine did to horses, make them obsolete? And at first you think, nah, we can't. We're too smart. It's too hard to do what we do. Well, more and more things machines are doing pretty darn well. And so, I see overall the opportunity of machine learning to help us solve models faster. So we can think about the economics, we can do the more creative, and all this like really painstaking programming and debugging. Maybe someday a lot of that we will do that a lot faster, and this space, the pace of science and structural estimation will actually increase. So I think I'm going to, I've gone from 4:30, it's now 5 o'clock. So I have 50 minutes. Is that right? Someone confirm that? Yeah. Is that right? Okay. I'm going to skip over all these slides are on here, but I'm just going to say something. I put a cool article in Science by 3 leading cognitive science. And, in some sense, you might sense in my talk, like, wow, these computer scientists are racing way ahead of us, and they're doing so much amazing stuff in artificial intelligence. They're just leaving the economists behind. And, what do we have? There's nothing left for us. I mean, we're going to all be obsolete. But, if you look at the rationality, both machine learning and structural econometrics are taking this concept of a rational robot. Machines learning, it's trying to create the rational robots, and it's doing it remarkably well. Things like, but it's very practical, and that's what's, I think, is really important and great about machine learning. Like, looking at a mammogram to see if there are tumor cells there, and it used to be done by radiologists and medical doctors, still is, but they're finding that a deep neural net processing a mammogram is more accurate in detecting tumors than people are. So that's a big win, but it's a practical goal. Now, what we're doing, largely economists are still stuck in some sense on the idea that people are rational robots. And, I'm going to be telling you later, I just don't think that's true. But, it sounds like I'm very critical of my own brethren here. But it's a pretty good starting place, and the benefit of like having this unrealistic assumption of perfect rationality and rational expectations, game theory, Nash equilibrium, is there really some interesting, very well-defined starting hypotheses, and that the work of mathematicians and economists have actually contributed to the AI. So when we talk about dynamic programming, well, when you look at Google and deep Q networks, they're solving a Bellman equation, right? They've adopted dynamic programming. It's just that they're solving it where none of us could solve it before. They're using some really creative techniques, and then they're solving, or approximately solving the Bellman equation, and that's why AlphaZero is the world's, best chess player now. So that's cool. And so this article on computational rationality is written by these cognitive scientists, including this guy Joshua Tenenbaum at MIT. And I'm not going to read all of this, but they give a lot of credit to economists and mathematicians, and particularly von Neumann. And this kind of path-taking book that they wrote with Morgenstern in 1947, Theory of Games in Economic Behavior, where they introduced expected utility and the idea of maximizing expected utility and probability and all the things that we, are now second nature to us. That came in 1947. And so there's a number of quotes. I'm going to have to go faster through this. But, you could say that, sometimes I look at what I'm doing and I say, what's my value added here? I'm using these dynamic programming. If I don't really believe people are really rational, and there's a lot of irrationality. I mean, in my, there's QAnon in the United States. There's people who are vaccine, a presidential candidate that thinks vaccines will kill you, like just crazy stuff out there, right? So, why model everyone as rational if you don't think they're rational? And, so we're just rationalizing. And, the identification problem that someone will probably talk about this week, says, yeah, you can always rationalize any behavior as optimal. And you can find, if you don't put much restriction on preferences and belief, you can always rationalize it as optimal, So what's the purpose of that? What are we really learning if we're doing that? So, but there is a value, though, to trying to build a rational robot and put some restrictions and say, how realistic could it be? So that's what I'm going to move to now. I'm going to talk about Bayesian learning and this, but I just want to show you this picture. This is John von Neumann. He's one of my heroes. He died way too young. You can see he was 54, and he's standing by one of the first digital computers in the world. He built it at the Institute for Advanced Study. That's where Einstein was, Gödel. I mean, unbelievable. And they were horrified. They were pure math people at the Institute in Princeton. And they were horrified that he would build an actual machine in their pristine theoretical, Shangri-La. But he did it because he was getting funding from the Department of Defense to simulate a nuclear bomb explosion because of the Manhattan Project days. And he was going to do, simulating nuclear explosions in the day, but at night, artificial light, cellular automata, all sorts of really good science. So that was the devil's bargain. And if you look at those little cylinders that's down there, that's the RAM on that computer. There was, it was like a V24 machine. It had 5 kilobytes of RAM, and von Neumann was so happy and proud of his achievement. Now now we call it the von Neumann machine, and the main reason we do that is because unlike previous machines where you had lots of wire, you had to rewire to do a program, they store the memory and the data in the same place. It's you can just reprogram the computer through registers in the memory. And so now this idea of the von Neumann has been refined and refined. And here's a quote I like from this. And just in March of 1953, there were 53 kilobytes of high-speed random access memory on Earth. That's from George Dyson, Turing's Cathedral. Very cool book about this. What von Neumann did. Oh, how much RAM is there now? There's about 200, if you believe this, 295 billion gigabytes, and the amount of memory is going up by 10 gigabytes per second. Just think about that. So we are refining machine, and now we're on the verge of quantum computing. So like unbelievable increase in power. And my M1 Max, and I'm doing this from an M1 Max, and I realized now it has a GPU, and now I'm really motivated to get Python and PyTorch because I could run PyTorch, and my GPU has 32 cores, and it can do something like 10 teraflops. That's 10 trillion floating point. That's why people are using GPUs, and they're under really short supply. Well, anyway, that's enough of computer geekiness, but I hope to geek out this week and really use PyTorch and learn from John Stachurski. Now I'm really motivated. I've been using MATLAB, but I think I'm going to switch because MATLAB does not support GPUs on my M1 Max Pro. Okay, so I'm going to go, Simone talked about the neural net. It's artificial. You have, our computer's based on transistors. Our brain is based on the neuron, much slower. And, basically he talked about the McCullough pits where you got the dendrites and the axon fires, and the cell body there kind of is like the summation. So that's kind of, it's empirical, the McCullough and Pitts, you can say they looked at, stains of neurons, and they built an abstract. It's way simpler than an actual neurons. And the actual neurons are so much more complicated. But this brilliant observation has led to so much with these deep neural networks. So I'm going to skip, and now I want to talk about, and here's another hero, Herb Simon, bounded rationality and limited cognition, cost of cognition. We got to go there. We got to go there. And, to really understand what humans do, we have to look at the fact that our brain runs on only 10 watts of energy, and that we're lazy for a good reason, because using a lot of mental energy is costly biologically to our brains. Okay, so I won't have time. I wish I could talk about all this stuff, but let's talk about something, practical. So these are more of my heroes. This is dynamic programming. These are the guys that developed the theory of perfect rationality. So now here we are. I think I have enough time to go through this. And I'll try to go a little bit slower, but let me stop for a minute. I've been droning on. Does anyone have any questions, or can everyone still hear me? Or are you all sleeping now?
No. Everybody can hear you, John.
Okay. All right. Am I talking too fast?
Right.
Okay. So I'll try to talk a little slower. But are people Bayesian? I think this is kind of a classic. To me, it's a cult classic. It was published in the Journal of American Statistical Association. It's by Mahmoud El-Gamal. He's actually a friend, a former colleague. We used to be at University of Wisconsin together. And David Grether, who unfortunately has passed away, but he was at Caltech. And he did a lot of work on Bayesian learning. And this experiment is a very cool experiment. They got 257 subjects at 4 California universities, UCLA, Pasadena, Occidental, and Cal State. And they gave them a bingo cage experiment. Okay, so you got these the circles there are like the bingo cage, and there's balls. And in cage A has 4 balls that are marked N and 2 that are marked G. So the probability of N is 2/3. And the other cage is 50-50. It's got 3 N's and 3 G's. Now, the way they did this is to get Bayesian learning in a controlled experiment is they had a 3rd cage with balls numbered 1 through 6. And what they had is one student would serve as a monitor. So to be credible that they weren't joking on the and trying to mislead the students, they would draw a ball from the what they call the prior cage, and they say, well, if I get a 1, 2, or 3, we're going to draw from cage A. If I get a 4, 5, and 6, we'll draw from cage B. So thus there's a credible prior that there's a 50% chance of drawing the balls from cage A. Now, the monitor, didn't reveal the draw from the prior cage, because otherwise they said, well, I got a 2, you'd know it came from cage A, so it would be stupid, right? But what he would do is just nod and say, okay, they're doing it correctly. And so once they drew the prior cage, determine which cage A or B the sample would come from, then they would draw 6 balls with replacement from the chosen cage. Okay, so 6 balls are sampled with replacement, and the subject's job is to say which cage, A or B, did the given sample come from. Okay, so if, for instance, if the 6-sided die lands 3, 4, 5, or 6, then cage H. So now it's got a 2/3 chance of being chosen. That's the prior. Okay, so that's the nature of the experiment. Let's see if so. Basically, now the prior, we normally think of the prior as subjective, but now that's something under experimental control. It's induced. So I'm going to call pi A is the prior that the students were, the credible prior that KJ was selected, the probability that KJ was selected. And then N is the number of balls marked in. So, since it's IID, order doesn't matter, and a sufficient statistic is just how many balls with the letter capital N come out in the sample, and we'll let little n denote that. So the information that the subjects have to do is this I, the prior and the draw observation. Okay. Now the subjects were paid a flat fee, but some subjects were paid a bonus of $10 for selecting the correct cage in a randomly selected trial that the subject. So it's not a lot of money. I would these days pay a lot more to kind of, because the critique of these experiments is, the cost of mental effort. You don't want to think about this too hard unless you're getting paid a lot. So you might say that's not a lot of money, but this is 20 years ago. So they have what are called a pay treatment and a no pay treatment. But a really important thing here is there was no pre-training of any kind. They explained the rules, and there was no ongoing feedback. So when the subjects are making it, they didn't learn which cage was actually, they found out after the end, they get some money for, if they selected the right cage. So it was a no feedback experiment, and that was a conscious experimental design. Okay. So let's just see if you want to try it. I have put a URL. Anyone who wants to go online, we'll announce this later. But we're going to suppose the prior, say it's credible that there's a 2/3 chance of drawing A, and we get our 6 balls are going to be N, G, G, N, N, and G. So there's 3 N balls. So little n is 3. So what would you say? What cage is more likely, cage A or cage B? So it's kind of like, I know you all know Bayes' rule. But maybe just doing it on the fly, maybe some of you are scratching with a pencil and paper, but why don't you try to just use your intuition and go online and answer A or B, and then we'll tell you later what people think, and we'll tell you shortly what the real answer is, the right answer. Okay, the Bayesian answer, I guess, would be the answer. So how did El Gamal and Grether do this? They use something called a cutoff rule, very natural. It's just an integer from, see, you can get any ball from 0 to 6. And if you get, so actually the cutoff rule should go from -1, because you could, you want to basically say if the number of balls is strictly greater than C, you can't have more than 7. So it should actually go from -1 to 5. So the idea is that you choose cage A if you get enough N balls, because cage A has 2/3 N balls. So if you have sufficiently many, you should choose A, and then otherwise you should choose B. But what you want is the prior to also affect that threshold. So the threshold C should be a function of the prior, and there's 3 priors in this experiment: 1/3, 1/2, and 2/3. So now we'll let C pi be the cutoff rule corresponding to the prior pi. So you have different cutoff rules for different priors if you're Bayesian. So for instance, Bayes' rule, if you work it out, and later we will, there's 3 cutoffs, 4 for the 1/3 prior. So you need more evidence to select A if you have only 1/3 prior chance. If it's 50-50, it's 3. And if you have 2/3, you only need two balls more than 2 balls to say it's cage A. So Bayes' rule is 4-3-2. It's these 3 cutoff rules. Now, what they observed is there's like 2 to the 21 possible, that's 2 million possible decision rules that are maybe not cutoff rules, but there's only 8 to the 3rd or 512 possible cutoff rules because there's the monotonicity. So that's what they treated, is they're going to assume, they're going to restrict the cutoff rules, and they're going to estimate what cutoff rule best describes people's behavior. Okay, so now we're going to generate a likelihood function. So this is where it may be a little bit taxing. There's a lot of notation here, but let me try to explain it very simply. Since you have a sufficient, so a subject, it's panel data. Subject S plays up to 20 trials. They repeat independent draws and they make 20 choices. So T is trial T, and we're going to denote if they're using some cutoff rules, C1, C2, C3 for these priors, the observation XS of T of C will just mean it's 1 if it's consistent, their choice is consistent with that cutoff rule. Now, it may not be consistent with a cutoff, any given cutoff rule. So, but you know, we need to have some kind of error mechanism here because there's no single cutoff rule that's going to explain all the subject's behavior choices. So we get something called a zero likelihood problem. So we have to introduce some kind of error to make a positive probability of any outcome. And so the one they chose is a kind of a, you know, interesting one. They said that with some probability, the subject, so epsilon, the subject just guesses, and they guess 50-50, you know, they flip a coin. But with probability 1 minus epsilon, they're going to use the cutoff rule. So it's kind of like a tremble or something, but, you know, they just give up or something. And so that's what they do. And so if you look at this page here, here's the likelihood. These are the XS of C is the total number of observation trials of the 20 trials. How many are consistent with a given cutoff rule C? C is the triple, and that you can either be consistent with the thing because of 1 minus epsilon, but it's 1 minus epsilon over 2 because you could also have not been consistent but just guessed. So, you know, you could have guessed right or guessed wrong. So if you think about it, it's, you know, 1 minus epsilon over 2 to the XC, and then epsilon 2 or the 1 minus XS of C. And the maximum likelihood is just the cutoff rule, which is this triple of integers, and then the error rate that maximizes the likelihood. Now, I'm going to talk about subject heterogeneity for a minute, but let me show you some data. And then come back to this. Here is the experimental design. And this has a lot of similarity to a confusion matrix in the machine learning literature. So what I have is on the x-axis, the prior probability. So there were only 3 priors, 1/3, 1/2, and 2/3. So that's why all the dots. And then on the y-axis is the number of balls marked n. And then the size of the circle is the proportional to the number of observations, and the colors are colored where if you chose A, if everyone chose A, it's red. If everyone chose, you know, in a given dot chose B, it'll be deep blue. But if it's a mixture, it's kind of purple. Like, you know, like in the U.S., they talk about the red and the blue. The Democrats are you know, the blue, and the Republicans are red, and then there's purple states. Well, a purple state is where there's a lot of confusion, right? And you can see the confusion's occurring naturally right on the boundary. The black line is the boundary that Bayes rule. If for, you know, if the prior was continuous, anything above that black line, that step function, is when you should choose the posterior probability is greater than 1/2 for A, you should choose A. So, you know, the other thing you should think about machine learning is, oh yeah, support vector machine or discriminant analysis. Can I draw a hyperplane to separate? And it looks like, yeah, I could draw a hyperplane there to separate those points. So maybe this isn't such a difficult task for machine learning. Okay. Now, what's really cool is accounting for heterogeneity. This paper was kind of ahead of its time. You know, it's 1995. They developed an algorithm called EC, the estimation classification. See, the likelihood I just gave you assumes all the subjects are homogeneous. They're all using the same cutoff rule. But what, you know, so we can think about, you know, what Simon calls unsupervised learning. Can an algorithm go in and discover their types, which are unobserved? We call it unobserved heterogeneity. So what if there are different people using different cutoff rules? Can we find an algorithm to, you know, machine learning, another one, to discover their types? And they, well before, machine learning is common, their algorithm is called the estimation classification. And, basically what it is there's a lot, equation one is, it's a likelihood where there's an outer loop where you fix a number of types. So maybe capital K, you have two possible triples of cutoff rules and possibly two different error rates. And for any choice of these pair of cutoff rules and error rates, you loop through everybody in the experiment, all 257 people, and you evaluate the likelihood for these K different types, like type 1 and type 2, and say which one is higher. So if the likelihood, so one might be Bayesian and another might be what's called representativeness. Like if the sample looks like the urn, you'll choose that and you ignore the prior. So then you'd say, what's the likelihood they're Bayesian? What's the likelihood they're representative? And if the Bayesian one is higher, then you say, okay, that's a Bayesian type. If it's a representative, you assign it. And that's what the delta hat. They're indicators that assign you to the highest likelihood, each individual by individual. Okay, so and at the end, you can then say how many people are Bayesian and how many people are representative. That's what equation one, and they maximize that. And then they could gradually increase the number of types until and they use the Bayesian information criterion, the model selection, to select the number of types in their model. Okay. Now, what you might think is, what about fixed effects? It's panel data, and how many parameters in this? Well, there's three parameters for the cutoff rules, which are integers, and then this error rate. There's 4 parameters, and if you have 20 observations, well, you might say maybe I can get away with fixed effects. I estimate subject-specific models, and then I can use a kind of a basic. I think the machine learning people have ripped it off from stat literature. It's called k-means clustering, right? You estimate for every person a 4-dimensional parameter of vectors on the 20 observations. The fixed effect estimator, maximize person by person. Then you cluster them and then take the cluster means. Maybe you see 2 clusters and then you identify 2 types by k-means clustering. So we'll come back and compare that in a minute. But the EC method, the problem with fixed effects is what's called the incidental parameters. It's, notice way back since Neyman that we don't have, what we want is the number of observations per parameter estimated to be going to infinity. But with this fixed effects, we only have T over 4, if T is the number of time periods that 20, so there's kind of 20 over 4, 5 observations per parameter. Whereas with, if you have a large number of subjects, it's ST over 4K, and as S goes to infinity, the number of observations per parameter is going to go to infinity with that, and so it will be consistent for an estimator, whereas fixed effects is not. So then there's a Heckman-Singer, another way of getting unobserved heterogeneity, and that is what's called random effects, where we estimate probabilities. We don't go through subject by subject and assign them to a type. We just say there's a probability mu1 to mu k that you are one of these 2 types, a Bayesian or representative, for instance. And then you maximize this mixture likelihood in equation 4, subject to the constraint that the probability sum to 1. Okay. Now, here's the empirical findings. If you start out with only a homogeneous model, there's just k equals 1, they find out that, hey, voila, 4, 3, 2, that maximizes the likelihood. So the subjects are making choices consistent with Bayes' rule. On the other hand, the bad news is the error rate is pretty high. It's 38%. So 38% of the time, they're just randomly guessing. Now, why would they do that? If they can behave according to Bayes' rule, what makes them just kind of randomly get? Are they spacing out or something? They can't be looking at their iPhone because they didn't have iPhones in 1995. So something happened. I don't know what was going on. Now, if they allow 2 types, the EC algorithm finds that Bayes' rule is the most frequent And then representativeness, which is the 333 cutoff, is the next most. And so 63% are classified as Bayes rule, 37% of the subjects as representativeness. And if you allow 3 types and then basically, Bayesian information criterion doesn't want to select any more than that, then you find that the third is something called conservatism, which is excessive weight on the prior, not looking enough at the data. So using likelihood ratio, they strongly reject the subjects behave in similar ways and they behave differently across the pay and no pay. So the subjects that were paid had a lower error rate. That makes sense, right? They're exerting more mental effort because they have more incentives. The ones that are not paid on a flat, why not guess, right? Because what difference does it make, right? After a while you get bored and you stop, like the baby looking at the ball, it's no fun anymore. Okay, so here's their conclusion. The answer to are experimental subjects Bayesian is no. The answer to what is the most likely rule that people use is Bayes rule. The second most is representativeness. Okay, so now I'm going to refer to them by their initials just because I don't want to keep saying Elgamal and Greth or EGG, egg. Okay, and I show you that. Now, I want to think about another model, right? So here's a critique. Now, Mahmoud is a friend. In fact, I'm going to try to convince him to be a co-author on a reanalysis of this. And so, 3 of the students here are well, 2 of them, Simone and Jeremy, they were subjected to this in my class. I taught structural econometrics this spring, so they've seen this before. But if I'm critiquing it just to help also teach different ways of modeling things, right? So I'm going to now try to go to more machine learning and say, how can we model this with, well, structural and then machine learning? Now, the question is why does people randomly guess? So the interpretation of the error term, may be a little problematic, so, you would think people would likely guess when the subjective posterior is close to 1/2, when you're kind of 50-50, but when you're really certain it's cage A, your posterior is really close to 1 or 0, well, why are you going to be guessing then? It should be like type, the type 2, right? The knee jerk, it just says, yeah, that's clearly cage A. And you just, so you shouldn't be flipping a coin then. Now, the other thing is this cutoff rule doesn't reveal the underlying beliefs. It's just revealing a cutoff rule, but there's a subjective probability. It's like in discrete choice models, we want to infer utilities. Okay. And we want to try to understand how is this payment, it's, reflected in the error rate, but could we get more drilled down into how payment, effort, the cost of effort, and, can we use insights from deep learning and machine learning to model how people are making this? Now, the final thing I'd say about it is the cutoff rules are not good for counterfactual, right? If I, suppose I change the number of balls in the urn from 6 to 10, which they did. They ran another experiment in Wisconsin, at the University of Wisconsin, when Mahmoud was there, and they wanted to kind of avoid, kind of an anchoring thing. And so this representativeness rule was prominent, but it was kind of easy because if you get 3 and 3 and one of the urns had 3 and 3, it's easy to kind of match it. So they put 10 balls in the urns to avoid representativeness. Now, well, if you estimated 4, 3, 2, or even if you had just 6 balls, but suppose you have a prior of 1/10. Well, you don't know what would be the cutoff rule toward, we can calculate with Bayes rule, but if you just estimated 4, 3, 2, you don't know what people would do if the prior probability is 1/10. So there's these problems with this model. And I think that, I think they're, acknowledge that. I'm not trying to be critical here. So let me talk about conditional choice probability. So, the EGG is a structural model because it was derived from a coherent theory of how subjects make choices, cutoff rules, and with mistakes. Now, we could use reduced form models, and Bob Miller will be talking about CCPs, and we're going to be talking about using deep neural nets to give us these CPPs shortly. So I'm going now at 1 hour, so I have 20 minutes, right? 20 minutes, so I got to speed up a little bit. You never have enough time, but I'm going to basically, I'm not going to talk a million miles a minute. People can read these slides, but here is a reduced form model, which you can also say is the simplest possible feed-forward network. We call it the logit model. The people in computer science, they call it the softmax, which sort of annoys me, because my thesis advisor was Dan McFadden. It's the multinomial logit model, please. And by the way, softmax is, even Wikipedia says that's not right. It should be soft argmax, right? The log sum function is the softmax. And so this probably is the soft argmax. It's the probability of choosing something, okay? Yeah, that's just a little joke there going on. But there's 3 parameters in this. So, you put n and pi into this logit model and just think about it as a flexible functional form. And then, there's no interpretation for it. And so we can think of it as a logistic squashing function, and it's a single layer feed forward network with 2 inputs, 1 output, and the logistic squashing function. Now, it turns out that this logit model fits better than the egg model. Okay, if you look at the likelihood, it's not a nested model, but I'll show it to you visually in a minute. The egg model has a likelihood of minus 1942. The logit model is minus 1800. Okay, now if I do a 2-type egg model, the likelihood goes from 1942 to 1699. But if I do a 2-type logit model with these 3 continuous parameters, beta 0, beta 1, and beta 2, I get even better than 1699. And I'll show you visually. So here's the basic thing. The green line is the egg model, under Bayes' rule. In other words, first of all, the dotted blue line is the true Bayesian decision rule, which is, if your posterior is less than 1/2, you should say it's B. If it's, even epsilon bigger than 1/2, you should say it's definitely, you're not certain it's going to be A, but you're going to say it's A. It's more likely that it's A. I'm going to show you that's optimal. Now, the black line is the data. It's just a non-parametric, it's cell-based optimum for the different posteriors we encounter. So the x-axis is the true posterior probability, and then the y-axis is just a fraction of the subjects choosing KJ. So if they were perfectly following Bayes' rule, if they're all perfect Bayesians with no error, they would be following the dashed blue line. Now, the Elgamal and Grether model is the green line, and you can see that doesn't fit the data very well. And what it is that they have this 40, almost 40% error rate. So, they follow, Bayes' rule perfectly for 40% of the time, or 60% of the time, and 40% of the time, they flip a coin. And that just doesn't really match up with the data very well. So the reduced form, the blue line, that's the neural net, that's just fitting a lot better, as you can just see visually. Now, here's the 2-type egg model. Here's the advantage, and they get a lot of mileage. That's why the likelihood went from 1900 to 1699. So now there's the green line, which is 64%. But now this black, the piecewise linear blue line, that's the representativeness rule at the data. And when you take a mixture, 64-35, you get the dotted black line. And that you can see that's much closer to the solid black line. So the mixture of 2 types is getting us a lot of mileage. But if you take a mixture of 2 logits, you're getting it even closer. Okay, see now so there's a red type, which is, you could say that's the Bayesian type. It's kind of closer to the dotted blue line. And then the representativeness, that's that solid blue line, it's kind of like a linear function. And you take the mixture of those 63, 36, you get the dashed black line. Okay. Now, you can also do Heckman-Singer and gives you similar results, except, you know, the type 1 and type 2, their behavior a little bit different. But it's reassuring that all these things come pretty close, different methods of discovering, you know, you could say it's unsupervised learning. We didn't label these guys as type 1. It discovered their types. So I guess they, you know, machine learning called it unsupervised learning. It learned it. But if you do k-means clustering because of the incidental parameter, it doesn't look so good. So I'm going to just blow by that for a minute. So that's not a method, you know, to really recommend. Now, let's just ask a question. We're going to talk about dynamic programming here. Why should a person use Bayes' rule? Is it just because we were taught statistics and we want to be good students? You know, like the student's t-test, you know, I like that nerdy name. You know, should we just be Bayes' rule? Is that just like a moral quality? No. If you're greedy, you want to be Bayesian. And what you can show is that mathematically, the decision rule is a decision rule. There's a delta. You can think about what subjects are doing is they're being greedy and if they're getting paid, they want to maximize their expected payment. Now, even if they're not getting paid, they are maybe get psychological satisfaction for trying to do the right thing. So either way, they're trying to maximize something. Now, what you can show is if they get utility, that even if they're risk averse, they could be risk averse. The optimal decision rule is Bayes' rule. So that was kind of a problem set in my class, and some of you who didn't take my class, try to prove that. You know, it's kind of a nice application of the law of iterated expectations, is that Bayes' rule maximizes your expected payoff. Okay, now I've got 10 more minutes, right? Is that right? Someone confirm that?
Yes.
All right, you're all still there. I'm sorry. I'm sorry. I wish I was there. I I'm not being able to see your faces, but I'm sure you're kind of confused at this point. But hopefully you can look at my slides. So here's Bayes' rule. You know, we all remember how to do that. Here's, you know, you flip it around. It's the posterior probability of A given the number of balls and the prior probability. And what's kind of cool here is you can manipulate this into an alternative formula that Bayes' rule is equivalent to equation 8, which is a likelihood ratio times a prior odds ratio. And when that ratio is less than 1, that's when you want to choose KJ. So the posterior being bigger than 1/2 is equivalent to equation 8. And if we looked at the example that I gave you, and if you answered it, the correct answer, if you're a Bayesian, is that you should have chosen KJ, because the posterior probability is 0.58, bigger than 1/2. Now, what's kind of cool is you can manipulate this, here's there's a lot of information and variation with the number of balls. You know, if you take the ratio of the blue and the red line, that's the likelihood ratio. That's the evidence in the data. And then there's the prior odds ratio, and you're looking at both. So now here, I'm going to talk about a structural logit model. Now, what I can do here is I can write the posterior, I'm going to call this pi s. It's the, without the s, it's the true posterior probability. That's what I wrote down here, equation 7, no s. That's the exact Bayes posterior. But now I'm going to create a model of a subjective posterior that's going to nest the true posterior as a special case. So with a little bit of algebra, you should be able to see that this logistic squashing function here, with the log, I have the log of the likelihood ratio and the log of the prior odds, that Bayes' rule is going to emerge as a special case with the parameter beta, which is the beta naught is the bias, and the beta 1 and beta 2 are the weights. So when the bias is 0 and the weights are -1 and -1, so they're equal weights on the prior and the log likelihood ratio, you get the true Bayes rule. Now, if you then say, well, why do I care about that? if you look at equation 9, now let's add, I'm going to follow my thesis advisor, Dan McFadden, who put the random utility model. So if you get $10 for a correct answer, $10 times the probability, your subjective probability, that's the expected reward. And now we're going to add on a random error, epsilon A. So that's the distraction you get. And then if you chose B, you get 10 times the subjective probability of B plus an extreme value error term, and it's scaled by sigma. So when sigma is very large, it's not noise is dominating. When sigma is very small, you're doing mostly what an exact Bayesian would do, except you have a subjective posterior. So when you write this, I can get the equation at the bottom by a little bit. There's the middle equation is the binary logit, the softmax, if you will, soft argmax. But then I can write it as a logistic squashing function. And now look at this structural model. It's a logit within a logit, right? The probability of choosing A is a logit that depends on the subjective probability, the subjective posterior of A, which is a logit. And see, there's the 1/2 is the threshold, and the sigma, if you kind of work it out mathematically, as sigma goes to 0, this becomes like perfect Bayesian. In other words, if pi s is bigger than 1/2, pi s is bigger than 1/2, that's negative, and then it's going to minus infinity. So exponential minus infinity, the posterior, the probability of selecting E is 1, and if it's less than 1/2, the probability converges to 0. So this is the model, and so it's got an interpretation as a neural network. And now let's just show you the structural logit model, and it fits even better than the logit model. So there's the Elgamal-Grether. The red line is the structural logit model, and then I also do something called a noisy Bayesian model. The noisy Bayesian model is I use the true posterior, but I just tack on this extreme value error. Okay, so there's a sigma, but instead of pi s, I put the parameter restriction on beta that 0 minus 1 minus 1. So you're doing Bayes' rule, but you just have some noise. Now, what's really cool about this logit is it makes much more sensible predictions about where you're most uncertain when your posterior is close to 1/2. That's when you flip a coin 50-50. But when the posterior probability, the true posterior, is close to 0 or close to 1, you're pretty certain. And the model shows that it's monotonic in that true posterior. Okay, it's not going exactly like the dotted line, but it's much more plausible model than the threshold rule and their error structure. Now, let me go now to say a few things about. I have 3 minutes. So we have this 2-layer neural network, and we can generalize it. So we have a binary classifier. That's what they would call it. And one of the tricks that I'm using in the structural logit model is I'm transforming the normally a machine learning person just puts n and pi into their machine, their 2-level neural network. But what I'm doing is transforming the neural net by taking the log likelihood ratio, that's T of n, and the log prior odds, and I'm putting those into equation 11. And that helps the model fit better, and it has the benefit of generating a nested where Bayes' rule is a special limiting special case. So the equations 12 give me restrictions on the parameters where I get the exact Bayes' rule in the limit. Now, if we don't transform we get a 2-layer standard limit with n and pi instead of the transformed. But then you might say, well, why do we get these deeper neural nets? Well, here's a nice interpretation. You might say, how does the subject know how to compute log of the likelihood ratio? That's pretty complicated. And even the log prior odds, you think that people really do that. maybe they're just reacting to n and pi, but somehow their brain transforms that. So now with the idea of layers, well, let's add extra layers. So now we say, I'm going to use as inputs n and pi, and I'm going to add extra layers to the neural network, make it a 3 or 4 layer, because those early layers try to approximate the log likelihood ratio and the log prior odds. And then the last 2 layers do what my structural logit model does. So now we can see why there's gains from doing deeper neural nets, and we can relax some restrictions and potentially train our rule. Now, if I do these, pre-transform, it's, I recommend, don't turn your brain off when you do empirical work. Just because you have machine learning, you say, I'll let the computer do it. I'll turn off my brain. Not a good idea. I've seen so many stupid stuff from people saying, yeah, I can just turn off my brain. I'm going to let the computer do it for me. No way. You can't turn off your brain when you're doing empirical work. The machines are just not that smart yet. So I'm going to say that, you need to think about what you're doing when you're doing empirical work. And there's a lot more in these slides where I kind of make that point. I'm running out of time. But the thing is, I want to say one last thing. One theory of what these subjects are doing is, just suppose they are a 2-layer neural net, even with the transformation or not. How could we train these 5 parameters? How many observations? Well, we need 1 million, like we said, these subjects received no training whatsoever. But if we were going to train our machine, how many observations? We're going to give them the perfect Bayesian rule, right? So we can think about structural estimation is supervised learning. We're trying to make the neural net behave like a noisy human. But what if we train it like a perfect Bayesian? We could do that too. And it turns out, well, if you try that, and I do in my code, I have MATLAB code, which I'll post, when I have a chance. It only takes about 10 observations. Even, you have 5 parameters with 10 observations randomly chosen with the perfect Bayesian decision maker. This machine nails it. The machine nails it. It doesn't need a lot of observation. So it kind of strikes you, this is an easy problem. So let me skip forward and then give you the last slide, bottom line. First of all, what we get out of this is we can infer that this is a subjective posterior, and there's 2 models. One is my 4-parameter structural logit model where I make these transformation, and then the blue line is the 5-parameter model without the transformation, and they give me pretty much the same answer for the subjective prior. And notice it reflects what's called overconfidence. In other words, when the posterior is the true posterior is higher than 1/2, the subjects is even higher. They're more confident than they should be, than what a real Bayesian. And when it's less than 1/2, they're more confident that it's B than they should be. And that's a well-known psychological fact. So we've been able to reveal, if you believe it, their subjective beliefs from this approach, which Elgamal and Grether couldn't do. Now, so this is a well-known thing in psychology literature, so we're seeing it. But some evidence to the contrary is, I found a study by Holt and Smith in 2009, where it was done at UVA, where they did a similar experiment, but they directly elicited the posteriors with what's called a Becker-de Groot-Marshak mechanism. And here you see that, wow, there's no overconfidence really. I mean, or very modest. They seem to be, their subjective posteriors seem to be pretty dead on the dotted line, which is the correct Bayesian beliefs. So the bottom line is, when you see these results, you say, well, people aren't exactly Bayesians, but man, maybe maybe rationality's got more going for it than you think. So I'll stop there. I'm sorry for going 3 minutes over. I know you guys want to have lunch or something, but sorry for droning on. But that's all I have to say.